Okay, looking at Torricelli's law, and let's say if we sort of go beyond just the mere use of spherical and cylindrical tanks, and let's say that we have a cubical tank that is 6 feet on each side, and where we have the tank to be half filled with water. And we have a 1-inch diameter hole that's cut out at the base, and water begins to drain out. And it says using Torricelli's law, determine about how long it's going to take to empty the container. Okay, so you have the cubical tank or container to be 6 feet on each side, and we have it to be half full of water. So what we have for the initial amount of water, okay, you're looking at where we have the water level Y is going to be at 3 feet, and we have at the base of the cubical tank we have a 1/2 inch radius hole. So again, 1 inch in diameter translates to 1/2 inch for the radius. And so we have, in terms of feet, okay, just to have a consistency of units established, okay, we have the radius to be a 1/24 for the number of feet. And so we have for the whole area, okay, we have pi r squared, or in this case pi times the square of 1/24 of a foot. And so we come out to pi over 576, make that pi over 576 square feet. Okay, now we have also in the mix, okay, now for the cross-sectional area, okay, again we have from the top to the bottom, again we have a hole at the very bottom. But throughout, okay, you have the water to be contouring the edges of the cube, okay, until we have the water to run out through the hole at the very center. And okay, so we have right now, okay, so long as the water is contouring the edges, okay, we're looking at, once again, 6 feet on each side. And we have for the cross-sectional area, you're looking at the image being a square, and so we have for the cross-sectional area, okay, so you're looking at the square of 6 feet, or in this case, okay, we have 36 square feet. That is 6 feet squared, or 6 feet times 6 feet, so we have 36 square feet. Now, for what we have in the case of Torricelli's law, okay, so we have A of y, dy over dt is equal to negative a times the square root of 2gy. Again, the cross-sectional area, we have 36 square feet. Right now, I will include the units, but I'll get them out in just a moment. Now we have the negative of the hole's area. So we have negative pi over 576 square feet. And we have times the square root. And we have of 2. And for the gravitational constant, okay, now we have 32 feet per square second. And again, we're going to have times y, number of feet. And what's going to happen here is that for the change in y with respect to the change in t, you're looking at in terms of feet per second. And guess what? We have for the cross-sectional area and the area of the hole, we have in terms of square feet. And again, if I took the square root of the product of the units, square root of square feet per square second, you have down to feet per second, as would be prescribed for dy over dt. So just wanted to check for the consistency of units. All right, so looking at what we have numerically and just bypassing the units. So we have 36 dy over dt. And here I'm going to go ahead and simplify 2 times 32 is going to be 64. Square root of 64 is 8. And we have 8 over 576. And that's going to go to 1 over 72. So if I go ahead and simplify, so we're going to have negative pi. And again, the 8 from the square root of 64 divided by 576. We have over 72. And we still have that square root of y left over. And if I look at multiplying, what we have here, okay, say by negative 72 over pi, and it's multiplied by 72 divided by negative pi. And for what we are going to have in this particular case, right, so we got what is going to be negative 2592 over pi dy over dt is equal to the square root of y. And if I separate the variables, and that is to simultaneously divide by the square root of y and multiply by dt, we'll have negative 2592 over pi times the square root of y dy is equal to dt. And just looking at separating, so to say I have negative 2592 over pi, the reciprocal of the square root of y, I can write as y to the negative 1/2, and dy, again I have is equal to dt, and upon separating, I'll just go ahead and integrate on both sides. So looking at taking the antiderivative, okay, so for y to the negative 1/2, okay, so that's going to be, in this case we have 2 times the square root of y, okay, and if I multiply by negative 2592 over pi, at the moment I'm going to have negative 5184 over pi times the square root of y is equal to t plus c. And establishing things, alright, so again we have that at time 0, okay, we have the water level is going to be at 3 feet. So we have y naught is equal to 3. And guess what? If I fill in, we have negative 5184 times the square root of 3 over pi is going to be equal to c. So t is at 0, and automatically, okay, we have the value of the constant as such. So we have in our formula, and this is a bit redundant, but we have negative 5184 over pi times the square root of y is equal to t minus 5184 times the square root of 3 all over pi. Now, in terms of how long it's going to take to completely empty the container, so we have for y of t is equal to 0, well, guess what? We're going to have that the value of y is at 0, so we have 0 is equal to t minus 5184 square root of 3 over pi. And just taking what we have and just working out numerically. Okay, so we have 5184 times the square root of 3 over pi. So we'll have for t, okay, so you have 28, 58.1 seconds roughly, and putting in terms of minutes. Okay, so this will be about 47 minutes and 38 seconds. Okay, let's say that we apply Torricelli's law in the case of a conical tank. And we'll say that we have a conical tank that stands 12 feet high and that has a radius of 3 feet. And instead of being completely filled with water, we'll say that it is partially filled where we have the water level to be at 4 feet. Okay, so and just like the conical, or I should say the cubical tank from earlier, okay, we're going to have a 1-inch diameter hole to be cut out at the base. And once again, we have water to begin to drain out. And we want to determine not how long it's going to take for the water to completely drain out, but for the water to get to the 1 foot level. Okay, so we have, once again, okay, so you have a hole cut out at the bottom and just history repeating itself. So we have for the area, you're looking at pi over 576, since we're looking at the radius to be 1/2 inch or 1/24 of a foot, and you got your pi r squared. So you have pi over 1, made that pi over 576 square feet. And now looking at what we have in establishing, okay, so you have the structure to be 12 feet high, and water again starts out at the 4 foot level. And we're going to have the water from the top to approaching the bottom to be contouring, okay, the conical tank itself. And in terms of how the water level and the radius of the water level will correspond, you can think of a little bit of pre-calculus. Okay, so you say that like you have like assigning ordered pairs, like you have the radius and the level of the tank. Say at the top you have 0, 12, and once you get to the base, whereupon we have ry to be at 3, 0. Okay, so think of this as a negative slope, and we're going to be looking at not in terms of the change in y with respect to the change in r, as in the traditional change in y with respect to the change in x, but we'll be looking at the change of the radius with respect to the change in the water level. Okay, so we could say that we have for dr over dy, okay, so you have like r sub 2 minus r sub 1 over y sub 2 minus y sub 1, and just assigning, okay, so we say we have r sub 1, y sub 1 at 0, 12, r sub 2, y sub 2 at 3, 0, and for r sub 2 minus r sub 1, okay, you have 3 minus 0, y sub 2 minus y sub 1, we have 0 minus 12, and 3 over negative 12 reduces to negative 1/4. So you have the change in radius with respect to the change in y equal to negative 1/4. And for what we have in r and y, okay, analogous to what we have for the point slope formula that you have seen in pre-calculus, and we say we have r minus r sub 1 is equal to the slope, in this case, where we have the change in radius with respect to the change in the water level. You have times the quantity of y minus y sub 1, and you can choose to go with 0, 12 or 3, 0, either way, and we'll just go with 0, 12. But if you chose 3, 0, like have 3 put in for r sub 1 or 0 put in for r sub 1, you'll have the same equation for the radius. And we'll just say we have r minus 0 is equal to negative 1/4 times the quantity of y minus 12. And so we have r is equal to negative 1/4 of y plus 3. And I'll just run through this right quickly. See, if I had chosen 3 for r sub 1, if I chose the order pair 3, 0, we have r minus 3 is equal to negative 1/4 times the quantity of y minus 0, and guess what? Still come out to the same expression. R is equal to negative 1/4 of y followed by the addition of 3. And this will be carried over in the determination of the cross-sectional pattern. And if you notice, okay, if you were to go from top to bottom, okay, and again you had that hole right in the middle, and you got, let's say, like the tip of the cone itself, but as you're going from top and getting closer to the base, you're going to have the edge of the water to be contouring, okay, the conical tank itself. And just for the cross-sectional area, again, you have the imagery to be circular, so we're going to be applying circular area. So you have for a of y, we're looking at pi times the square of negative 1/4 of y plus 3 and going ahead and squaring out, so you're going to have pi times 1/16 of y squared. Outside and inside product, okay, we have negative 3/4 of y minus 3/4 of y, so this will be minus 3/2 of y plus 9. And taking what we have and applying Torricelli's law, I guess you have a of y dy over dt is equal to negative a, we have the negative of the whole area times the square root of 2gy, and we are going to have the same setup as what we have on the, as what we did with the cubical tank, okay, same numbers, okay, but for the cross-sectional area, again, so you have pi times 1/16 y squared minus 3/2 of y plus 9. And again, just history repeating itself. So again, we have negative pi over 72. Again, we had that case from the cubical tank to repeat. And if you notice, we have at opposite sides. And if you notice, we have at opposite sides, okay, you have pi's to cancel out. And if I multiply by negative 72, and that is so as to get out of the fraction on the right hand side. So we're going to have negative 72 over 16, so it'll be negative 9/2 of y squared. We have negative times negative is a positive, so that is going to be plus 108y. Then we have minus 288 and before I get too far ahead, again, I still have the dy over dt on the right. Okay, so you have that expression, dy over dt is equal to the square root of y. And if I separate the variables, so we have upon dividing by the square root of y and multiplying by dt, so we're going to have negative 9/2. So you're dividing y squared by y to the 1/2, so you have negative 9/2 times y to the 3/2. And we have plus 108 times y to the 1/2, and we have minus 288 times y to the negative 1/2. Quantity dy is equal to dt, and integrating on both sides. Okay, so we're going to have negative 9/2 y to the 3/2, and the antiderivative. Okay, now you're going to have essentially, okay, so you got 2/5 of negative 9/2, so that'll be negative 9/5, or negative 1.8 y to the 5/2. And we're going to have for 2/3 of 108, so that's going to be 72 times y to the 3/2. And then antiderivative, you have for 2y to the 1/2 times negative 288, so that'll be minus 576 times y to the 1/2, or minus 576 times the square root of y. And we have is equal to t plus c. And once again, for the initial level, okay, so you have y naught is equal to 4. So whenever t is at 0, the constant is going to be the result of what we have on the left-hand side as we plug in 4 for y. Okay, so as t is set to 0 and y is set to 4, we will have for the value of the constant, okay, that is going to end up at negative 633.6. And in terms of configuring how long it's going to take for the water level to drop from 4 feet to 1 foot. So if I were to plug in 1 for y, so you have negative 1.8 plus 72 minus 576. So I have negative 505.8 is equal to t minus 633.6. And if I isolate t, okay, so in this particular case, all right, so we're going to have the result to end up at 127.8 seconds. And so this will end up being about 2 minutes and 8 seconds.